So this video is very exciting because this is really our first deep dive into some more abstract theory as it relates to linear algebra and really understanding the power of matrices and how we can interpret them. So we're going to be talking about these things called linear transformations and more generally just transformations, but linear algebra means we're talking linear transformations. And in order to really understand these conceptually, we're going to need a couple tools. So the first thing that we're going to need to recall is how functions work way back from pre-calculus 1. So kind of generically, just as a reminder, a function is something that, it's kind of like this, we call it a transformation. It's kind of like a map. And what it does is it takes something, an element from what we call our domain, which is a collection of values. And most simply, we kind of think of these as x values. And the idea is that this function is like a machine or a map. And it says you take that x value and it goes into this function. And then out pops some y value, right? And this y value lives in the what we call... we end up calling it the range. It's technically not correct to call it the range. It actually lives in this thing which we call the codomain. Okay, and I'll explain maybe what that is in a moment and how it differs from the range. But just to just bring a quick refresher, a simple function would be like you plug in an x value, you get a y value. And so typically, right, the very basic examples when you first learn about functions way back in high school or maybe early college, is that your domain is typically like, values that we get from the set of all real numbers. And your codomain is also, values that we get from all real numbers. Now, why do I keep saying this thing codomain? Why don't I say range? It's because now that we're a little older and more mathematically mature, range means the possible output values that we could get from a function. So the range is actually like a bubble. It's like what we call a subset of the codomain. So the range is all possible outputs. All right. And so what that means is, like, let's for instance think of the function y equals x squared. Okay, so let's think of f of x equals x squared. The domain of that is all real numbers. It is the domain is all real numbers. I can put any x value that I want in here. What am I going to get out? Well, I'm only going to get out positive numbers. I'm going to get out from this thing all positive numbers and 0. So you can kind of think about it as if this bubble is like all real numbers, then the codomain is all real numbers. Codomain is all real numbers. But the actual like possible values that we could get live up here, and this is like all non-negative numbers. Right? All non-negative numbers. Because that's what we can really get out from this function. Okay, so those non-negative numbers, right, our output, those numbers live in the set of all real numbers. If the set of all real numbers is this entire bubble, right, the set of all real numbers is everything, our possible output values, what we call our range, is a subset. It's part of this. So in this class, we're going to start making a distinction between the fact that our range, in this case, our range is what we call a subset. Our range, in this particular example, is a subset, or like a small collection inside of the codomain. Now, sometimes, the codomain and the range are the same thing. So, for instance, maybe we have a simpler function, f of x is equal to just x. So this is just a straight line, y equals x. And again, the domain is all real numbers. And the range is the same thing as our codomain, right? Because you put in any x value and I'm going to get every single possible y value that you could. And, so our codomain in this case is equal to our range, right? The space where all of our possible outputs live are the exact same. So all of our possible outputs that we could get, could cover this entire space. So that's like a distinction, but this should be something that we've been fairly, used to. And these functions that we learned about, we learned once you took multivariable calculus that it doesn't just have to go from R to R, right? We don't just have to go from the set of real numbers to the set of real numbers. And so as an example, the surface, right, or you could just say the function given by, x squared plus y squared, right? Z is equal to x squared plus y squared. What this is, if you think about it, what is our domain, right? What is the domain of this surface here? Well, the domain here, I can put in any x value and any y value that I want. So the domain here is all of R2, right? It's anything that we want. It's any x and y that I could put into this function, this surface, this mapping, if you will. And what are all the possible z values, the outputs we could get out, right? So in this case, you can think about how, this takes a two-dimensional thing and it maps it to a single z value, right? It takes it to a single z value. So the codomain here, the codomain is just the set of all real numbers. That is where this output lives, right? We have two inputs, one output. Great, we go from R2 and we kind of shrink down to R, if you will. And so now what's the range of this? Well, again, very similarly to the x squared example above, we can only get positive or non-negative z values. So like, you could just put a blob in here and just indicate that this is the range. It is a subset of all real numbers. And the range is, all z in from 0 to infinity, right? That's what it is. And that is like a subset. It's a piece that lives inside of our codomain space, the set of all real numbers. Okay. Now, another way we could have viewed this instead, right? We could have said, okay, maybe what I want to do is I actually want this thing to map to the 3D point x, y, z. So if you decided to look at this in another way, you could say that the domain, again, is R2 space. It's collections of x and y's. And you could say that our map takes us to R3 if you wanted, right? It takes us to R3, our codomain, and it consists of all of these points x, y, z, right? You could define the mapping in this way, where z, right, where z is still equal to x squared plus y squared. This is a another totally fine way of thinking about this. And what possible points, what kind of possible points could we get? Well, this would be kind of like the upper half of 3D space, right? Because we can plug in, we're going to get any x, any y, but these z values can only be positive. So if you think of our codomain being all of R3, right? All of R3 looking like this, then the codomain is basically everything, that's the XYZ axis, or excuse me, the XY axis and above. It's like all this space. And then all the space under it is outside of our range. So our codomain would be all of R3, right? That's where our possible outputs live. But, the range here, the range is still smaller, and it's like the upper half of R3, if you want to just kind of be loose with it. Okay, so this is just kind of like a refresher of what functions are and how they work. They take in inputs, they have outputs. You may remember from the review assignment, there's things that we have to worry about, like if a function is onto, if a function is one-to-one. And those are things we're going to consider here pretty shortly. But for right now, we're just talking about like functions or these maps. They take things from spaces, from one space to another. And I'm introducing kind of this new topic, this codomain and range. I'm making kind of this distinction between them. Okay, so if that kind of makes sense and that refresher feels good about what a function is and how they work, then we're going to define this thing called a transformation. Okay, so a transformation, I'll use colors, a transformation, which is sometimes called, or a function. It's also called a mapping or mapping. Kind of all used interchangeably, but for this class, we're going to use the word transformation. A transformation, which we're going to call it T. We're going to call this transformation T. And the way that we denote where our domain is we write it like this. Our domain is going to be, it's going to be some space. We're going to say it's Rn. And then we're going to say that it maps to another space Rm. Now, these could be the same space, just like if we scroll above, right? We could go from R to R. They could be different spaces. We could go from R2 to R. We might go from R2 to R3. That is denoted basically right here. So if we have a transformation, we call it T. This is like the equivalent of having a function and calling it F. This first thing here is our domain. This right here is our codomain. Okay, so a transformation T that maps from Rn to Rm is a rule. It's a rule that assigns each vector in Rn, or I guess I'll call it X, each vector X in Rn to a vector, we'll say T of X, I guess I should, T of X, and that is in Rm. Okay, we call this vector, so we call T of X, this vector T, we call T of X the image of X under the transformation T. Transformation T. Oops, no bar there. T. Okay, so that was a lot of information. So again, let's think about it. The idea being that in linear algebra, the concepts are still very much the same. We are going to start in some space. It's going to be our domain. Okay, let's pretend, it's generally speaking, this is n-dimensional space. But, for the sake of just keeping us grounded, let's say that we define a transformation from R2. So it takes a generic vector that has x1 and x2 in here. And T, transformation T, maps it to where I plug in my vector x. Remember, this is my vector x equals from R2. I plug this vector in to my transformation, plug it in, and then what do I get out? Well, I'm going to get out some new vector, and just like in regular algebra, we would get f of x. Out here, we're going to get a vector t of x. And I put an arrow over here to indicate, t itself. The reason why I don't have one here is because t is a transformation. It's like the name of the transformation here. But right here, after we've completed this, this is now a new vector. And that vector is, what dimension is it? Well, it depends on where we're mapping it to. So in the examples I gave earlier, you notice that we could start in R2 and end up in R. We could start in R2 and end up in R3. I could start at R2 and define something super crazy that ends up in R107th. So let's just say, for the sake of example, let's just pretend that I'm doing a mapping to R3, right? Then this generic vector over here has components, maybe I'll call it B1, B2, and B3, right? And that's the idea. You plug in some sort of vector into T, and you get out what we call the image of T, right? This right here is the image, excuse me, not the image of T, the image of the vector X under the transformation T, okay? So that's a lot of fancy words, but a transformation in general is just, it takes a vector in, pops a vector out, the end. Not too bad. And the way that this is typically denoted is we use, like basically, or let me back up a second. The thing that does this changing, right? Like in algebra, we just like f of x equals x squared, or f of x equals the square root of x minus 3, or f of x is equal to sine of x, right? We create stuff. But how do you map a vector to another vector? Do we have anything that says you plug in some vector and you get out some new vector? And it turns out that we actually do. And so transformations are typically defined by matrices, defined in linear algebra, using a matrix A. Okay, and we have no idea what that means, and I'm actually just going to jump in and give us just an example, okay? So here's the idea. So, by example, what the heck's going on? Okay, so example. This is how you would see it worded, and we're going to break this down, and it's going to start making a lot of sense. So a typical way this might be worded is consider the transformation. Let's call it T. And let's say that it's going to go from R2 to R3, because that's what we just did. And we're going to define it. So defined, we're going to define this transformation by saying that T of X, right, my output, is equal to AX, where A is the matrix, and let's come up with something to say. Let's do 1, 3, -1, and -3, 5, and 7. Okay, so consider defined by this. Okay, and so typically, by the way, an alternative way of denoting this is we say like a vector X is mapped to is going to be mapped to some output given by AX. So this in English is saying the vector X maps to the output, or the image, AX, where AX and T of X are the same thing. Now, there's a lot of stuff written down here that I haven't explained, and I've tried explaining it different ways before, and the best way is to just do it via examples. So what does this mean? What does this mean? This right here is the equivalent of me saying f of x is equal to the square root of x minus sine of x or something, okay? That's what it says. It's saying, look, we have a transformation. It takes in some sort of vector. It takes in a vector. How do I define what the output is? Well, back in algebra class, we just created something here. We created something absolutely at random and said, all right, see what this does. Let's graph it. Let's get some information. Where are the maxes? Where are the mins? Where's the concavity? Let's do all this stuff. Where is it going? What shape does it look like? and can we sketch it, things like that. In linear algebra, the equivalent is multiplying by some matrix. This matrix, this is very important. We are now viewing this matrix as like a special combination of numbers that you plug a vector into. The matrix A scrambles things, and it maps it to a brand new vector t of x, or a times x. So what do I mean? Okay, so like let's take a look. Okay, so let's consider, or actually we already have the transformation. So let's just say, evaluate t of x, where and sometimes the book doesn't have this arrow here, but I'm just going to keep it because I like it. So evaluate t of x, where the vector x, let's say, is the vector 1, 2. Okay. So what this means, here we go, picture time, theory. According to this transformation, we are starting, our domain is here. It's R2. And we are picking the vector 1, 2. X is equal to 1, 2. Okay? We have a transformation T that is mapping it from R2 to R3. So we expect that whatever it is that we get out is going to live in what space? That our codomain here is going to be R3. That our output vector should be some 3D vector. So whatever it is, let's call it, it's going to be the result t of x, and that's going to be some 3D vector that I have no idea what it is yet, but that's what we should get out. Okay, how do we actually get that? Well, t of x is defined, right? T of this vector, 1, 2, is defined, it is literally defined by A times that vector. So we have the matrix A from earlier that we just made up completely at random in the same fashion that I just made square root of x minus sine of x at random. It is completely at random. And I have this box of numbers, 1, 3, -1, -3, 5, 7. And we have that we multiply this by the vector 1, 2. That is literally the definition of what it means to be this particular transformation. So this should look very familiar in the sense that this is like our matrix A, this is like our vector x, and it's going to pop out some vector b. This is a very important concept that I just wrote down. Transformations, eventually we're going to talk about what makes them linear or not, but just for right now, transformations are another way of viewing this equation ax equals b, which originally came from a system of equations, which originally came from vector equations, which originally then became a matrix equation, and then we used it for things like linear independence and span and blah, blah, blah. Now this thing can also represent a transformation, where this is our input and this is our output, okay? And so there's a lot of technicalities with how we view this notation, and it is historically a little complicated, so feel free to post lots of questions in the discussion. But to evaluate this thing, all we really need to do is we need to figure out how to multiply this matrix, which is a 3x2 matrix, multiply it by this 2x1 vector. And you'll notice that the dimensions do agree, the fact that because this is a 3x2 matrix, and a 2x1 input vector, that our output vector should be a 3x1, right? It's going to be something. There's going to be a b1, a b2, and a b3 here that we expect to get. And so the question is, how do we get that? So to answer this question, we need to tackle one more concept, which is matrix multiplication, because I've tried to do this without explaining this, but it's impossible. So matrix multiplication. How do you actually multiply a matrix times another matrix or a vector? Because we already know, I mentioned that there's this rule I mentioned that the insides have to match to make this work, and as long as the insides match, then we can actually do it. And so the way matrix multiplication, as we've seen it before, it would be if I took this matrix A that we've been given, and I called the first vector V1, called the second one V2, right? We would do this, and this one we know how to do. This one we would do the multiplication. We just do a dot product, and we would get like 1 times my V1, so 1 times V1, and then plus 2 times my V2. And this, if we expand it out a bit, is going to be just, this is 1 times the vector, times our vector 1, 3, negative 1. And then this is going to be plus 2 times the vector negative 3, 5, negative 7. Okay, great. This is a very long-winded way of doing this process, and I'm trying to show you something that's kind of interesting. And the one thing that I want to show you is that if we do this, this ends up being a system of equations, right? This ends up being, if I really wanted to write this out as a system of equations, this would be like 1, it's kind of silly to do this, but I'm just going to do it anyways. 1 times 1 plus 2 times negative 3. It's like the first entry. The second entry would be 1 times 3. And then over here, we're going to have like a 5. I'm just going to kind of jump these down so I don't have to swap colors the entire time. And then we're going to have plus 2 times the 5. Then we have a 1 of this and a 2 times this. Great. Awesome. And so something interesting here that you may or may not notice that's actually happening here is that when I write it like this, it turns out that this is the exact same, that what we will get is the exact same as if I had taken this row right here and done a dot product with this column right here, and that creates the first entry in this new vector. That's very important. This is matrix multiplication. The way matrix multiplication works is that it turns out it is the exact same thing. Instead of going about this long-winded process just to get here anyways, it turns out that you can just take the first row here and the first column here. And since we know that that's going to be a 3x1 matrix, that's going to create the first entry in our new matrix if we do the dot product of those things. And sure enough, we're going to have 1 times 1, and that's going to give us this guy. And we're going to add it to negative 3 times 2. That's going to give us that part. That gives us our first entry. And we can keep doing this process. If we do the next one, 3, 3, 5, that row dot this column, we get this one. And if we do this row dot this column, we get the last entry as is. So matrix multiplication is defined via kind of a row dot column process. And I'm not going to do this rigorously. There is actually a rigorous definition, and I may write it down in a future video. But the idea is that if we want to do a matrix multiplication, this is the way that it is defined. So maybe I'm going to just do a brief example here of what would happen if I took this matrix 1, 3, negative 1, negative 3, 5, 7, and let's say I multiplied it by something slightly bigger, maybe a 2 by 2, which not only had 1, 2 in it, but maybe it has 3, 4 in it as well, because this is still a 3 by 2, 3 rows, 2 columns. This is 2 rows by 2 columns. So now we expect the answer to be a 3 by 2, so 3 row and 2 column answer. We expect to have something here, 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 here. So how do we go about figuring out what goes where? Well, I claim that the way you do matrix multiplication is I'm going to take this first row and this first column, and it's going to go right there. And then we're going to take the first row and the second column, and it's going to go right there. So row 1, column 2 goes in row 1, column 2 over here. If I take row 2, column 1 in the first one, it becomes row 2, column 1 in the solution matrix. If I take row 2, column 2 in the multiplication, it becomes row 2, column 2 over here, and etc. So if I'm actually doing the operations for you all, we're going to get, for the first one, we're going to get the dot product of 1, -3, and 1, 2. So we're going to get 1 times 1, which is 1, plus -3 times 2. So that's 1 minus 6. So we're going to get -5 for this first entry. Then we do it again for the first row, second column. So I'm going to get 1 times 3, which is 3. And then -3 times 4, which is a -12, and 3 minus 12 is a -9, and so on and so forth. So we move on to the second row, 3, 3, and 5, and then 1 and 2. So 3 times 1 is 3, 5 and 2 is 10. That makes 13. Then we do 3 and 5 times the 3 and 4 vector. So 3 times 3 is 9, 5 times 4 is 20, so we get 29 here. And then last but not least, -1, 7, and then dot the 1, 2 column vector gives -1 plus 14, which is positive 13. And then we get -1, 7, and 3, 4, so -3 plus 28, which I believe is positive 25. And this is the solution. That's it. This is how matrix multiplication is defined. It is stemmed. You could go the long process of shrinking it to get it to look like this first form I introduced to you all last week. But it turns out the more convenient way to do it is just row times column, row times column, row times column. And this only works if the insides match up here. Okay, so if this is in your notes now, I'm going to, maybe I want to erase it, but I'll zoom out here and I'm going to move it down because I really want to go back to this transformation that we were talking about because that is way more important. So let's go put this down here. Okay, let's get back to this transformation. We were considering a transformation from R2 to R3 that is defined by this particular box of numbers. Now, I haven't talked about how do you get this box of numbers? Is there strategies? Do certain boxes do certain things? Again, this box of numbers is equivalent to me making up a random function. I'm saying that this matrix A is acting like how a function would act back in algebra class, where basically this transformation is defined. T of x is defined by you take the vector x and you multiply it by the vector A. And so this question that we're trying to answer here, evaluate T of x, where x is the vector 1, 2, means that we are simply going to take this matrix A and we're going to multiply it. We're going to multiply it by our vector x here. So since things line up, then it turns out that T of x, so T of x, we already know is going to be a 3 by 1 vector. And so we're just going to do row, column, row, column. So if I do row times column here, we're going to get 1 times 1 is 1, and then -3 and 2 is -6, so this is going to be -5. Then we do the next one over, so we get 3, 5, and then 1, 2. So 3 times 1 is 3, 5 times 2 is 10, so this gives us 13. And then last but not least, we have -1, 7, dot 1, 2 again, and so -1 and 1 is -1, 7 and 2 is 14, that's going to give us a positive 13. And so it turns out that this particular T of x here is this vector -5, 13, 13. Okay, it lives in R3. So we have mapped an input vector from R2, and we have now an output vector that exists in R3. Now, there's probably a bazillion questions you all have. There's some very natural questions, such as, okay, well, in algebra class, if we have y equals x squared, we know that the output of this is all positive numbers, right? It's only going to be the positive numbers. It's like half of r. Can we do something similar with this? And it turns out the answer is yes. Remember that this transformation T of x is defined. It is defined by a times x, or in other words, going back to our handy dandy notation, AX equals B is basically a representative of our transformation. So our transformation T, so A and T, this is a very important thing. A and T are not the same. T is our transformation. A is the thing that kind of makes the transformation happen. So analogously, f of x equals sine of x. You don't say that f is sine, right? You just say f is the name of the function, and f of x, right, the happenings, the machine or the guts of this machine is the sine function itself. Or maybe you wanted to make it plus the square root of x. Then you would say that the guts of f is sine of x plus this square root of x bit. So you wouldn't say that f equals sine plus the square root symbol. That doesn't make any sense. So in the same way here, A is just, it is our box of numbers. But the idea here is that x is our input. A is kind of like our machine, okay? And then B here is our output. And so a very natural question, right? B exists here in our codomain. Some very natural questions would be like, for instance, well, what are all the possible outputs we might get, right? What are all the possible B's that we could get? And that should hopefully ring some bells in the sense that like, oh, so what you're saying is we have a matrix and then we have like something of coefficients here. And we're trying to ask, like, what are all the possible B1, B2s, B3s we could get? Like, will it be all of R3? Will it be like a subset of R3? Will it be a plane, a line? Will it be just a one vector? And that should kind of ring some bells for talking about like span and linear combinations and things of that nature. So I'm going to stop this video here. I think this is plenty to chew on just for this. What you should take away from this video is that transformations are just things that map vectors to other vectors. You have domains, you have codomains, you have a range, which could be a small piece of a codomain. It could be the entire codomain itself. We learned how to do some matrix multiplication in here. And more specifically, we learned that now that matrices act as kind of like the guts of a transformation. They allow transformation to happen. They are the representations of transformations. And in future videos you're going to see this week, you'll see that certain transformations, certain matrices will do things like rotate vectors. They'll stretch vectors out. Maybe they cause them to flip certain directions. Maybe they cause them all to stretch and move over, right? So depending on the combination of numbers that we have inside this box, it turns out that it'll do different things to our input vectors, and that could be very interesting to us. So yeah, we're gonna end this video here. I hope it was kind of interesting, and we'll pick it up in the next video.